I think for the general public, transmutation is transformation of lead into gold. That's the real word, the signification of transmutation. Anyway, actually my affiliation is maybe correct, maybe not, I'm not sure, because I retired the university 6 years ago. I should have put retired in parentheses, but I forgot to do that, you know. I still think I'm teaching or working at the university. Anyway, I have to tell you a little story before we start. In 2000, you know that during their stay in France at IMRA, Stanley Pons and Martin Flashman did a large number of very successful experiments. Unfortunately, very little has been published. And maybe it will be lost for eternity. They developed a new calorimeter, the ICARUS 9. And this calorimeter, I will give you a few details later, but has a capacity of running at boiling temperature for long periods of time, because they realized that there was a positive feedback in cold fusion, and then you go to higher temperature is better. So they realized that when they did experiments to the boil-off experiments in their ICARUS 2 cells, they got a lot of excess heat during the evaporation of the water. So they developed this calorimeter for that purpose. In 2001, I mean, that was already, the lab was already closed there in Sophia Antipolis. In 2001, Stanley Pons gave me a cathode, and he said this cathode produced a lot of heat. So I had it in my drawer for years, actually. And actually, a few years ago, I remember, but where's Mike McCubry? Because I have something to tell him. I gave him a piece of this cathode, said, you have a mass spec, you should check for helium, because helium will not be desorbed, because there's no driving force for helium to get out of the metal. Anyway, I kept that electrode, and last year, I met someone in Montpellier, someone working in Montpellier, and he had a SIMS machine. I don't know if you know what the SIMS is, maybe you're not familiar with that technology, but basically it's a mass spectrometer where you can etch the surface of your material and look at the different peaks as you etch the surface. So as soon as I discovered that person, and he had a Cameca 4F, which is very good quality equipment for that, I asked him to do the experiment because I was thinking that maybe there is silver, anomalous silver in the palladium. I had no idea what the palladium was, I mean, how pure it was, because I didn't have the original sample. So let me give you a few details now, because well, I have to have time. Okay, this is the ICARUS 9 calorimeter. Okay, I have to divide myself in two, because I have to give indications on one side and the other side at the same time, you know. Well, anyway, this is a regular, inside this, there is a Pyrex tube here that goes all the way down, and in this Pyrex tube, you can put a Palladium electrode. It can go up to 10 centimeter length. With the anode, it's not represented here, anyway, and do electrolysis. But the idea here, it's kind of heat flow calorimeter, very simplified heat flow calorimeter, because there's a double wall, and there is an insulated layer in between the two walls, and you can measure temperature inside inside and outside. So there are two thermocouples here, two temperature sensors, whatever it is, on both sides, so that you can measure temperature inside and outside. So you have an estimation of the heat flow. Now, when you reach boiling temperature, depending on the power, the vapor will condensate on the top and fall back. So if the power is medium, in the medium range, you will be sensitive to this level. And if you have a lot of power, then you will be sensitive at this level. So you have 3 levels of working for this device. The whole thing is in a constant temperature bath. Actually, I met Stan Pons a few years ago, and he gave me the drawings of this, the original drawings, and the guy who manufactured these things, we finally found it 20 years later. He was still alive, the glass blower also. And I made 2 copies of this apparatus, thanks to international heat. Industrial heat, not international. That may be international too, either way. Maybe they don't know it yet. Okay, now, I have to tell you a few things about palladium and the silver. Okay, palladium has, I don't know, six isotopes. All are, 5 of them are odd numbers, and one is, no, even, one is odd, I'm sorry. So as you can see, 102 is only 0.96%, 104, 11%, I'm sorry. 105 is 22%, 106, 107, you can read. Now, if you add a D2 to a palladium isotope, you will produce silver 104, which will immediately change into palladium 104, which is natural. Now, same thing with palladium 104, you go to silver 106, will go into palladium 106, so you never notice it. Now, you have palladium 105. Now, if you put deuterium, then you get silver 107, which is stable, obviously. And same thing for palladium 106 goes to 108, 108 goes to 110, and 110 goes to silver 112, that goes to cadmium 112. Now, I was thinking maybe with that reaction, we can find out the mechanism. So I thought maybe we produce neutrons, so let's see if we add 2 neutrons instead of adding proton and neutrons. So that's the next slide. So now if you do the same thing with neutrons, dineutrons, you get exactly the same thing. Basically, you get not silver 107, but you get palladium 107 that has a very long lifetime. It's almost stable. It's beta stable. I mean, we're talking about millions of years. So at the scale of the 20 years of the cathode, should be there. So it's just a problem with short and long. You never know, it depends on the scale. Anyway, so we should get about the same thing, if it is dineutron or if it is deuterium. So there's no way to understand the mechanism with that kind of analysis anyway. But as you can see, you don't have silver 109. Okay. It's not there because there's no silver 109 with this mechanism, with deuterium or with neutrons. And actually, silver 109 and silver 107 are about 50-50. So we should see a difference if we produce silver 107 and not 109. So this is a photograph with my iPhone of the part of the electrode. Originally it was 100 millimeters by 2 millimeter, pure palladium. How do I know it's pure palladium? Well, I filed one piece of the palladium, a few millimeters, so that I could analyze by SIMS the bulk of the palladium. And there was only palladium. There was no silver at all. There was nothing else than palladium. It was pure. I think Pons and Flashman worked a lot with pure palladium, not with alloys. Now these are some electron microscopy pictures of the electrodes, so you can have some idea of how it looks like. I don't know if that can help you, but I took them and show it to you anyway. I mean, if I didn't do it, I would not feel good, you know. This is. Everybody does that. You don't understand, but you do it. Is that true? How can you see anything with that? Even Ed Storms cannot see the cracks there. Is that true? It's not too small. So there's no use to look at it, but we do it anyway. Okay, analysis. So it's a dynamic SIMS. There are all kinds of SIMS, but this one is dynamic. That means you can do depth profile, which is very important at the University of Montpellier. We use an oxygen beam to etch the surface, so we can make a profile. Now, when I talk to, sometimes I shouldn't talk before, but I talked to Peter Agatstein about this experiment. And he said, well, maybe you have deuterium in the volume, so what you're looking at is palladium-deuterium molecules. So I decided to heat it up in air to remove all the deuterium that's inside. So I'm sure there's no deuterium. So that's what I did. So I'm sure now, where is Peter? No doubt there's no deuterium in my cathode. So now there's no more deuterium in it. Calibration. So I wanted to calibrate the depth profile. So I used a 100 nanometer film of palladium deposited on silicon wafer. If I had time, I would explain why I did that. That would be interesting. I need to talk to people that work at, with the previous talk on the wafers on the nickel and copper, you know. That's very interesting. Anyway, though I could calibrate the system with that. Before going further, I have to tell you that I went twice doing the analysis. The first time, we checked and we found spots where there were 10 times more 107 than 109. That was before heating in air. So I knew there were spots that were a lot of 107, and unfortunately when you do mass analysis, there's no tag on the spectrum telling you this is silver. You just see peaks. You have to interpret these peaks. Anyway, so I knew there was 10 times more 107 than 109. So after heating in air, I did the analysis, and well, here it is. In the mass spec, I mean, the vacuum chamber is never really vacuum. There's no thing like absolute vacuum. There's always some traces of hydrogen. So you can find mass 106 due to the palladium 105 plus an hydrogen, or mass 107 due to 106 plus hydrogen, or 109 by 108 plus an hydrogen. Palladium 106 is 27.3%, palladium 108 is 26.7%. Basically, if we produce molecules that are palladium 106 plus hydrogen or palladium 108 plus hydrogen, it's about the same ratio as the silver 107 and 109. So this kind of interference should not change anything. So now I've done the profile analysis, and so sorry, it's seconds, it's in French. You can translate it yourself. Remove the E. So anyway. So the top line is the top line is the palladium 106. The red line is silver 107, and the green line is silver 109. So that's one spot. Now second spot, different. Now the 107 is much higher, is one order of magnitude higher than the 109. And when you etch, after a while, they'll both go to zero. As I was telling you, in the bulk, there is no silver. No peak 107 and 109, I have to correct. This is an interpretation. When I got before having my PhD, I met the director of the lab. He said, one thing you have to remember, always separate experimental data and interpretation. Because experimental data will remain, but interpretation will change. And I have to be careful. So I didn't see silver 107, I see mass 107. I have to correct that. Now, if I correct that by assuming that there is the silver, the peak 109 is due maybe to a palladium hydrogen molecule, and I subtract it, so it remains only the 107. And here it's corrected into nanometers the time. Now, profondeur means depth, for those who don't understand. I have to translate, these Americans don't speak French. So now you see that the depth profile shows you that the peak 107 disappears after about 1 micron. So for my friend Ed Storms, I will tell him that for me, the surface is 1 micron depth in this type of electrodes anyway. So that was not enough for me. I was hoping, I have to tell you, these are hotspots. I mean, you don't have that everywhere on the surface. You have to find it. So I decided I should send my sample for analysis in a laboratory that can really measure silver. So there is a laboratory in France which is dedicated to that. So I etched the palladium in aqua regia, took the liquid, sent it to the laboratory. That cost me 400 euros. But they gave me, after 3 weeks or 4 weeks, the result of the analysis. The lady was not there. She was on leave. I don't know. It's a long story. Finally, I found out that there was an increase of 3 thousandths of silver 107 compared to 109. So I was really disappointed. I was hoping there would be 10 times more, you know, but there was only 3,000. So these results are in agreement with other previous works that have shown that there was silver in the palladium electrodes. Also, but I made a mistake. I didn't analyze mass 112. The guy who is running this lab in Montpellier is going to take his retirement 1st of July. So I called him. I said, I absolutely need to do this experiment before coming to ICCF-21. He said, I cannot, you know, because everybody is running to the lab to do experiments because I'm leaving, and there's nobody to take over after that. So I finally have an appointment for next week. So there's nothing I can do unless I can have a machine that goes back in past or in future. So anyway, so I will go and analyze for cadmium-112 because this is a key measurement. It has to be there too. So I think I'm done, no? Conclusion, okay. Now again, you have to be very correct, very, very careful with measurements in mass spectroscopy because you measure only masses, you know? It's just like the Higgs bosons, you know, they have seen just a bump. They have nothing, a tag with bosons, you know, in it. It's a bump. That's an interpretation, depending on your model. So anyway, that's, I think this is happening only in hotspots. And I have to do that again to measure mass 112. I think that's it. Thank you very much. I'm finished. I have time for questions.
Okay, we've got 3 minutes for questions.
Jean-Paul, very nice. If for some reason he goes on vacation early, I would be volunteer to take that sample to NASA and do that analysis. We've got both TOF SIMS and we've also got mass spec.
Okay, I will send you a piece.
Okay.
And we will do that. We can compare results. Very good. Thank you.
So could you go back to the interpretation of what the 107 came from again?
I don't know.
Oh,
I mean,
okay.
I think it's silver, but again, yeah.
Well, the silver comes from which reaction? The D, the neutron?
If
Yeah.
I know you cannot make the
You
difference
cannot.
because you see same mass with neutron or with deuterium. That's a problem. Yeah.
And then the 3/1000th.
Yeah.
Since it's only partly on the surface in spots, why would you expect it to be, you know, any more than that? Right?
Well, you know, I'm very optimistic by nature. So
Okay.
I wondered maybe there'll be some anomaly, you know, that will be rubber stamped by an official laboratory like CNRS. But 3,000 is just the limit of the standard, the deviation there is in nature for silver.
Thank you, Jean-Paul, for an entertaining presentation. If you can assume that the products of LENR are non-radioactive, or they won't decay, regardless of whether it's a long period, maybe you could consider favoring the silver rather than the neutron-induced option. And from a energetic point of view, palladium exchange reactions, the maximum is 3.3 MeV, and the production of silver 107 is 12.8 MeV.
Yeah, but again, this is a secondary reaction in this cold fusion reaction. I mean, the main reaction is more like production of helium, so I don't think it matters too much about the calorimetry of the system. That's my understanding.
You've actually pointed out a very important thing here. You know, you're washing a surface off with aqua regia, you're then setting the sample out. We know from almost all the other work that people have done, particularly using SEM-EDX, that you get little localized hot spots, and so you get completely washed out by the background. So a general question for the community here is, I have been dying to find somebody who's built a device with an SEM-EDX, obviously under vacuum, with a laser ablator that feeds into a mass spec. So you find the area of an elemental anomaly, and then you feed that into the mass spec so you can do the isotopic anomaly in the spot where it is, so you don't get washed out by the background.
Yeah, but you know, the spots are very small, just like...
well, ours have been on the order of about 50 microns.
Okay.
We used something similar, actually. It's moldy, but it doesn't work with element weights below 90. It needs molecules then. And you use a UV laser, and it breaks stuff off on a spot.
You mentioned that the Palladium 107 was radioactive.
Yeah.
I would check for radioactivity to see if that 107 matched the spectrum for the radioactivity coming from 107.
Well,
from
there's
the palladium.
so little 107 to start
Well, you can
with, and
activate
the 1
it.
million years
There's good schemes for
half-life.
neutron activation that'll make that 107 shine like the North Star.
Okay, I don't have any equipment to do that yet. Maybe I buy one of these days. Okay, thank you.